Okay, so I think the screen should be visible now, right? Yes, no?
Yes, ma'am, it's visible.
Okay, so just a brief recap. We were looking at linear programs and in particular duality. So we saw some examples of how the dual can be written, and we looked at the minimization as well as maximization problems. And the idea is similar, like what you want to do. And yeah, so we went over some examples and some interpretations that the dual could hold. Okay, and then yesterday we were looking at this weak duality concept, so which is just the consequence of the way the dual is defined. Okay, so if you have a primal as a minimization problem and the dual naturally becomes a maximization problem, so what you have is for any primal feasible point and a dual feasible point, if you take this B transpose Y is going to be less than or equal to C transpose X. So it's going to be a lower bound from the dual feasible point. And in particular, the dual optimal, which we refer to as D star, is going to be always less than or equal to P star. Okay, so now using this, we looked at different possibilities of the relationship between the primal and dual. Okay, and so where I left off last class was if you have the case where the primal has a finite optimum, then what are the possibilities for the dual? Okay, so dual unbounded was not possible from weak duality, and the dual cannot be infeasible. So that is something you can prove using Furka's lemma. So I hope you guys will try it out. So this is going to be a sure question for the exam. Okay, so yeah, I'm telling you a question beforehand itself. Okay, so that's something you should try, and we'll focus on this case where the primal has a finite optimum and the dual is feasible. So there is also and it has a finite optimum. Okay, so in that case, we were looking at this duality gap. Okay, so it's basically the difference between the optimal, primal, and dual problems. Okay, so this duality gap is always going to be greater than or equal to 0. Okay, that's just a consequence of weak duality or the way we define the dual. Now, in particular for linear programs, it turns out that the duality gap is exactly 0. So meaning that the primal and the dual at optimality, they have the same objective value. Okay, so this is known as strong duality. When this happens, this phenomenon is referred to as strong duality. Okay, now this concept of duality is a very general concept in the sense that for any constrained optimization problem, there is a dual problem. Okay, so we will come to that once we start constrained optimization. Okay, so even over there you have these notions of weak duality and strong duality. So in general, weak duality is something that always holds for any constrained optimization problem because of the way it's defined. But strong duality, this concept of the primal optimal and the dual optimum carrying the same value, that is not guaranteed always. Okay, in general, it's never true. But here we have a class of linear programs where always you're going to have strong duality. So this is irrespective of the parameters A, B, and C that define the LP. Okay, so for this class of linear programs, strong duality is going to be maintained. Okay, so there are a lot of useful implications as a consequence of strong duality. So before we go to that, let's just try to see why this is the case, why the primal and dual have the same optimum value, okay, for linear programs. Okay, so let me begin. So I'm in particular going to look at this as my primal form. Okay, and this is the dual optimization problem. Okay, so the min is the primal is of the min form. Okay, so our assumption is that the primal has a finite optimum called P star, and there is a value X star, okay, which achieves this primal optimum. So its P star is just C transpose X star, and the assumption is that dual is feasible. Okay, so with this assumption, let's see what happens. Okay, so now because you have P star and there is the dual defined in this way, weak duality always holds. Okay, so any dual feasible value you take, you're going to have B transpose Y is going to be less than C transpose X for all primal feasible values, and in particular, it's going to be less than C transpose X star, which is exactly equal to P star. Okay, so this is true for all feasible, for all dual feasible Y. Okay. Um, so now the question is whether whether you have a Y in this feasible, in the dual feasible space, which satisfies that B transpose Y is equal to P star. Okay, so if you have that, then it means that the primal and dual optimum are the same. The optimum values of the primal and dual are the same. So to check this out, what I will do is I will look at this other system where this is true. B transpose Y is always going to be true for every Y. So let me look at the system where I look at the feasible Y's, A transpose Y less than or equal to C and Y greater than 0. So this is just the dual feasibility. And in addition, I'm going to enforce that this B transpose Y is greater than or equal to P star. Okay, so I'm defining a new system here, and what I'm trying to do is I'm going to check whether this system is feasible. So if this is feasible, it means that you have found a Y, for which B transpose Y is exactly equal to P star, because it cannot be strictly greater than P star because we know that weak duality holds. So the only way that this can be feasible is when B transpose Y, when there is a Y such that it's exactly B transpose Y is equal to P star. Okay, so the investigation is on whether this will have a feasible solution. Okay, so if it does, then we have proved strong duality. Okay, so let's just see what happens. Now, one thing that helps us is Farka's lemma. So just to recall that, so the system that we had there is exactly one of these two systems are feasible. There were two systems of which exactly one of them is feasible. And the systems were something of this form. So the first had some A tilde times Y less than or equal to D and Y non-negative. Or this other system where A tilde transpose Z is 0 and some B transpose Z is less than or equal to 0 and Z is non-negative. So these were the two systems. Okay, so I'm going to apply this Farka's lemma variant onto this system. Okay, so for let me just that's infeasible. Okay, so suppose Y is infeasible. Okay, so I want to see what goes wrong or whether something will go right if Y is infeasible. Okay, so that means the system doesn't have a feasible solution. So now what you can do is you can represent this system. Okay, this is the system marked 1. You can represent it like this. Okay, so how would you do that? So basically you want everything as inequalities, like less than or equal to form. So can you tell me how you can do that? Guys, am I audible? Are you all here?
Yes, ma'am, you are audible.
Okay, so can somebody tell me like how do we represent this system of equations in this form? Like I want tell me this value of A tilde and D. Right? What's going on?
Ma'am, can we just include the B transpose Y is greater than equal to P star into the A transpose and then write A tilde, just multiplying by minus sign and then.
Yeah, exactly. It says that, right? So what I will just do is we'll just rewrite this as minus B transpose Y less than or equal to minus P star. Okay, so what you will get as A tilde is just minus B transpose and A transpose, right? So this is the A tilde. Okay, so what this means, this B, so just to explain this a little more so that it'll be easier to, when you take the transpose of this. Okay, so this means B is a column vector. That's the usual representation. So B transpose is a row vector. So this would be something like this: minus B1 minus B2 and so on up to minus Bn. Okay, because in the original system there are m equations. Okay, so this B also there are m equations. So A, so this A here is actually okay, I don't, let me just write it here. So A is of this form, right? So we think of them as these m equations or inequalities. So these are all the row.
Ma'am,
But
sometimes your voice is breaking. Sorry to
oh,
interrupt.
Yes, ma'am.
okay.
There is a network problem on your side.
Rajnish, can you say that again?
Ma'am, there is network problem from your side.
Oh, okay. Okay, so I don't know what's happening. Seems like it's fully connected, but anyway. Yeah.
Sometimes
So
it
let
is.
me know. Yeah. So just let me know if it happens again or you're not able to hear. So I think some of you have my number, right? So just let me know in case I, drop off the call. Okay. So yeah. So what I'm saying is this A is represented in this manner: minus A1 up to sorry, this is A1 to AM, so not minus. So what I mean to say is that this is a row vector. Okay, and so there are m of them. Okay, so when you write A transpose here, what this is going to be is, A1 to AM comes here. Okay, A1, A2 like that. So all these columns come up here. Okay, so that is going to be this matrix A tilde. Okay, so now, so this is A tilde, and if you want to write the D's, so the D here is basically the right hand side. So D is just minus P star and C. Okay, so C is again, it's a column vector, so you have this in this form. Okay, so now the system, this first system is exactly this system Y here, the set Y here. Now this, if you write the second system, right, so what would that be? So I'm just going to substitute this A tilde transpose Z is 0 and D tilde times D transpose Z is less than 0. So what this would be is A tilde is exactly minus B transpose and A transpose, this times Z. Okay, so let's also write what Z would be. So here you see that there are again going to be, what is going to be the size of Z? Can somebody tell me? Anybody? Okay, so yeah. Does anybody want to attempt what's going to be the size of Z? So what's the size of A tilde? So
N plus
A,
1 comma M.
so this is going to be n plus 1, right?
Yes, ma'am.
Oops, sorry. I don't know if I removed some stuff here. Okay, so A tilde is just this. And this is going to be of size n plus 1 times n, right? A tilde is going to be of this size. Okay, so we're going to say this times Z. Okay, so so you can think of Z as having, let's just see what A tilde transpose is. Right, so it's just a transpose of this matrix here. So all the rows become columns. Okay, so first with minus B transpose, this whole row is going to come as, like this, minus B1, minus B2, like that, up to minus Bn. And you're going to have A on this side. Okay, so the first row is going to be minus B, and the second part of this matrix is going to have A. Okay, so just try to see why this would be, because now each of these, like A1 to AM, that is going to come on this side. So this first row here is going to be minus B1, and here you're going to have A A1 trans, so this one, right? This A1 itself is going to come here, okay, on this side. And then in the second row, you're going to have A2, okay, and so on up to AM here. Okay, so this is exactly A. So when we wrote A, this was exactly A1 to AM in the rows. So that's why this A tilde transpose is going to have this form minus B and A. Okay, so I'm just explaining this a little more for, I know some of you are not very comfortable with these transposes, and when we just keep taking transposes left, right, and center. So, okay, so in the A tilde transpose is going to be this. And so this system here would have, so B is one column, and here there are M columns. So there is M plus 1 times M. This is a matrix of this size. So you can think of the Z as having a component Z0 and another component W. Okay, so where this is a scalar, Z0 is a scalar, and W is in Rn. Okay, so Z overall, it is a system of size n plus 1. Okay, so you can take the column view. So let's just write this. So A tilde transpose Z equals 0. That would mean minus BA times Z0 W. This is 0. Okay, so this is actually system 2 is this. System 2 is what I'm writing here. So minus BA times Z0 W is 0. And D transpose Z. So D is just minus P star and C. Okay, so, and so let me just write it again. So D is minus P star and C. So when I write D transpose Z, okay, so what I'm going to get is, can somebody tell me what I want to say? D transpose Z is less than or equal to 0. So what does that amount to? Are you here? Am I audible?
Minus P, could you go back to slide? Minus
Yes.
P star Z0 plus C times W is less than.
Right. So minus P star Z0 plus C transpose W is less than or equal to 0. Right. So yeah. So one thing is, I think the system here was actually, this is strictly less than. Okay. So it was not less than or equal to. So let me just make that. Okay. So so here it boils down to this as less than 0. Okay. Strictly less than 0. And you have that Z is greater than or equal to 0. So that means Z0 is greater than or equal to 0. And each component of this W, so Wi's are all greater than or equal to 0. Okay, so this is what system 2 evaluates to. Okay, so now remember we started off with the system Y, and we assume that suppose Y is infeasible. So if this Y is infeasible, that means the system 1 is infeasible. So it must be that the system 2 is feasible. Okay, so that means there is a Z0 W which satisfies these equations. Okay, so what? Let's just see. Let's just try to simplify this and see what it means. Okay, so this would be. So let me just expand this. So this would be minus B times Z0. So this is a vector, Z0, and Z0 is a single number and W is a vector. So I'm taking the column view of multiplication. So where Z0 gets multiplied with the first column and gives you minus B times Z0, and plus A times W is equal to 0. Okay, so this is the first equation. And so this means, this just means that AW is equal to B times Z0. Okay. Now coming to the second inequality here. So this would mean that C transpose W is less than P star times Z0. Okay, fine. So I hope this is clear. I mean, it's just the simplification. So you also have Z0 greater than 0 and all the W's are greater than 0 component wise. So if the original system, the first Y is infeasible, then you have that this is feasible. Okay, this system must be feasible. Okay. So now let's just see what happens. What does it mean if this system is feasible? So in particular, let's take the values of Z0. So Z0 is greater than or equal to 0. So there are two options. So either Z0 is strictly greater than 0 or you have Z0 equal to 0. Okay. So now let's take the first one, Z0 strictly greater than 0. So that means you can again rewrite these equations. Okay. So if this happens, you can say A times W by Z0 is equal to B, and C transpose W by Z0 is strictly less than P star. Okay, and you have W and Z0 are both greater than or equal to 0, and Z0 is strictly greater than 0. So you have that W by Z0 is strictly, is greater than or equal to 0. Okay, so now the implication of this is that, this means that for the primal problem you considered, so the primal problem was minimize C transpose X such that AX greater than or equal to B and X greater than or equal to 0. So here is one feasible point. So W by Z0 is feasible for the primal. Okay, it's feasible for the primal because it has, A times W by Z0 is exactly equal to B, and W by Z0 is greater than 0. And in particular, you can see this objective, C transpose W by Z0 is strictly less than P star. Okay, so which means that originally X star is not the optimum. Okay, or the value P star is not the best value. Okay, so that cannot happen, right? Because that our original assumption is that P star is the optimum and X star is the one that meets it. Okay, so this case truly cannot happen. Okay, so now let us see what happens. Other option was Z0 equal to 0. Okay, so in that case, this system of equations here, AW equals BZ0, so that would mean AW equals 0. Okay, and Z0 is 0, so C transpose W is strictly less than P star. Okay, and you have W is greater than 0. Okay, so so this means that this vector W is in the null space of A. Okay, and so suppose then you take this vector, consider this vector X star plus W. Okay, so consider this vector, you can construct this one, and if you take A times X star plus W, so what you're going to get is X star is feasible, so this AX star is going to be greater than, this is greater than or equal to B, and plus AW, which is equal to 0. Okay, so this overall multiplication you do is going to be greater than B. Sorry, this is greater than B. Okay, and X star plus W is also going to be greater than 0. Okay, because NW is also greater than 0, X star is greater than 0. Now, when you take C transpose X star plus W, what you're going to get is C transpose X star plus C transpose W. Okay, and okay, so okay, I think I made some mistake here. Okay, so the contradiction has to be that this is going to be less than or less than P star truly. Okay, so I don't know what. So this is greater than or equal to B, and C transpose X star plus C transpose W is okay. I think can anybody see what the issue is? Can someone help me? Okay, are you all here? I don't know if I'm even audible now. Okay, am I on the network?
Yes. Hello? Yes, ma'am.
Yeah, okay, good. So I think the issue was about the application of Farkas lemma. So this is less than.
Suggested something. in the chat.
Do we take x star minus w? Yeah, so thanks Devyani for saying, for suggesting this, but actually I think the issue was this value, d transpose z less than 0 is what we had. So now, did I do that? D transpose, so minus p star, this was less than 0, okay. Okay, so this was, so C transpose W by, so this is less than, okay, so here this is the mistake that I made. So this value here, so we were looking at Z naught equal to 0. So if I write this, C transpose W has to be less than 0, not less than P star. Okay, so that's the mistake that I did. So yeah, so then when you, yeah, I think now it's fine. So when you take ax star plus w, x star plus w, if you take, you're going to get this value is greater than or equal to b. And this value is because C transpose W is less than 0. So overall, this is going to give a value which is less than P star. Okay, so now here is a new point, x star plus W, which is having a better value than P star. So that cannot be the case. Okay, because P star was the true optimum of the problem and X star was the one that achieved it. Okay, so this case also cannot happen. So in all, it means that this system cannot be feasible. The second system here is not feasible. So it must be that this first system is feasible, and it boiled down to this, right? This y equals of this form minus means B transpose y. So this was actually B transpose y greater than or equal to P star. Okay, so that was true. So this is feasible. So then that gives you that, you have a point y star in this. Okay, and so it must be that B transpose y star is exactly equal to P star. Okay. So yeah, I'll just pause for a minute and are there any questions? So I don't know if this proof made sense. Was it clear to you all? Guys, yes, no, you can type.
Yes, ma'am.
Yes. Okay. Some of the others, Nidish.
Yes, ma'am, it was clear.
It's clear? Okay. So please ask, okay, if something seems amiss. It's just a straightforward application of Farka's lemma. It's just you have to, just substitute the right values. It's just a matter of that. Okay, so I remember like sometime back when we did Farka's lemma, some of you were asking me like, where do we see it being used? It just seemed like, a dead end. But so you see here, these are some of the places. These are like some foundational results, and they've made use of Farka's lemma. Okay, so it's a very useful concept in general, the Farka's lemma, and you would see it also being used in general constraint optimization theory. Okay, yeah. So okay, so if this is clear, so what we have shown just now is the class of linear programs. They satisfy strong duality. Okay, so this idea has several uses. Okay, so we'll just see some of the consequences of strong duality and what you can do further with it. Okay, so one thing is the dual is many times used to detect if you have reached an optimal point. Okay, in the sense that when you there are a lot of these algorithms which make use of solving the primal problem by going through the root of the dual. Okay, so in general, the idea is, if you have found, okay, so this is the primal and this is the dual. So if you have found a point, so if you have found some x such that C transpose x equal to B transpose y, and AX greater than or equal to B, x greater than or equal to 0, and you have A transpose y less than or equal to C, y greater than 0. So if these conditions hold, if you can find an x and y pair such that this is true, that means you have reached, so this is for optimality, right? So if you, so this is satisfied only for some x which is optimal for the primal and some y which is optimal for the dual. Okay, so these satisfying this system of equations or these inequalities, these are not equations but inequalities, if you can satisfy these, then you know that you have reached an optimum. Okay, so this is something that gets used. I mean, there are these whole primal dual algorithms for solving linear programs, which make use of this idea. Okay, so it's also an iterative scheme where you start from a point in the primal, and each time you're trying to find a new primal feasible point, but it also maintains a dual feasible point. Okay, and so finally it stops when this happens. So simplex in that sense is not the only algorithm, and in fact the simplex algorithm, like there are some, I mean, it does well for a lot of cases, but there are some cases, a few cases in which the complexity can be quite large. Okay, so you can see some examples in Leuenberger. The specific example itself is given in Leuenberger. So that's why there are a lot of algorithms for linear programs, and some of them make use of the dual space. Okay, so this is about the optimality conditions for linear programs. So now another point that I want to mention here is that, take the X star and Y star that are primal optimal. Okay, X star is primal optimal, and let Y star be optimal for the dual. Y star is dual optimal. Okay, so now what happens is you have that AX star is greater than or equal to B. Okay, and if you multiply this with Y star, it's dual optimal, it has all these greater than 0, Y's are greater than 0, A transpose Y less than or equal to C. Okay, so if you multiply this with Y, what you're going to get is B transpose Y star is going to be less than or equal to Y transpose A star A X star. So this is Y star transpose. Okay, so it's the optimal. I'm looking at only the optimal points. Okay, so this is true, and by the feasibility of this Y star, it also means that this is less than C transpose X star. Okay, so this is exactly the thing that we saw. Okay, now so if you so if you take this, okay, now you can just, I'm just looking at this side, and I'm just going to say that Y star transpose AX X star minus B. Okay, I can do this. Okay, this is going to be greater than or equal to 0. Okay, so it's just, I just brought it this side. Now, this quantity here, this whole term here is less than or equal to, this part is less than C transpose X star. Okay, and you have a minus Y star transpose B, and that is exactly equal to C transpose X star. Right? And so that means this is less than or equal to 0. Okay, so what this is telling you is that Y star transpose AX star minus B is exactly equal to 0. Okay, so this Y star is now, I'm just going to expand what this means in terms of each of these vectors. So this is, you have m of these Y stars because there are m equations. So this would be Yi star times AI transpose X star. So this is the ith equation minus Bi. Okay, and this is the summation from I equals 1 to m. Okay, this is going to be equal to 0. Okay, and now this Yi star, this is greater than or equal to 0, we know, and this is also greater than or equal to 0 because X star and Y star are feasible. So what this means is that Yi star, so each of the terms in the summation also have to be equal to 0. Okay, so Yi star times AI transpose X star minus Bi, this is equal to 0. Okay, and this is true for every one of those equations, and this is what is called complementary slackness. Okay, complementary slackness. And this holds only for the optimum points. So X star and Y star, if they are optimal, then this relation is satisfied. Okay, is this clear? Let me just pause for a minute. Was this clear, like what I'm saying here? Yes, no?
And could you explain the last part again, the slackers thing? After
Okay.
the summation step.
This, you understood how we get the summation, right? The summation equals 0. That is fine.
Yeah, but how is the second part greater than equal to 0? Shouldn't the second, within the brackets, that should be equal to 0, right?
No, so this is just this is just the inequality, right? So it's ax greater than or equal to b. That is the original
Oh, okay,
problem we
okay. Yeah,
started with.
yes, ma'am.
Right, so each of these equations, I mean, each of these inequalities will be greater than or equal to bi. So ai transpose x star will be greater than or equal to bi for each of the i's, and that's why this is greater than or equal to 0. Okay. Yeah, so any
Yes, ma'am. And then after that, you explained about the slackers part. Can you explain that?
yeah. So each of these terms is greater than or equal to 0. So if you look at the y's, those are greater than or equal to 0. And the second term within the brackets, this is also greater than or equal to 0. And so you're adding up a collection of non-negative terms. None of these terms, if you look at all the i's from 1 to n, this product is never going to take a negative value. So the only way this can happen is that each of these products must be equal to 0. Otherwise, the overall sum cannot be equal to 0. Okay. So, so what this means is that for each inequality in your primal form, if you take the corresponding dual multiplier, this yi star corresponds to, for each constraint I, yi star is the corresponding multiplier, how you got the dual, right? You multiplied it with that yi. So at optimality, you will have that this product yi star times the value of this constraint ai transpose x star minus bi. If you take this product, that is going to be 0. Okay, so this is what is called complementary slackness. This condition that for all i's, for all the constraint, you're going to have this product as 0 is referred to as complementary slackness. Okay, so
Yes, ma'am.
that's fine. Okay, so what this means is that let's just look at this a little closely. So suppose the constraint. Suppose some constraint ai transpose x is strictly greater than bi. Okay, so then if this happens, so that means this term is greater than 0. It's strictly greater than 0. This difference is strictly greater than 0. So in order to make this 0, it must be that the yi. So this is all at optimality. Okay, so if ai transpose x star is strictly greater than bi, then it has to be that yi star is equal to 0. Okay, so there is no other go. This has to be the case. Okay, so so what this is telling
Ma'am, you aren't audible to us.
I think ma'am got disconnected. No, ma'am.
Yes, I think.
It shows ma'am is still connected, but
okay. Hi, am I audible?
yes, ma'am.
Yes, ma'am.
Okay, I think I got disconnected for some time. So what was I doing last when I was still online?
And you said that if ai x star minus b is greater than 0, strictly greater than 0, then yi star should be equal to 0.
Equal to 0. Okay, fine. So this part was fine. So all right. So this
Ma'am, the
will.
screen is not presented.
Oh, okay. Present. It's strange. Some network issues. Okay. Okay. So I think it should be visible now, right?
Yes,
It's
ma'am.
okay. Okay, and I think the call is recorded, so that's also fine. Okay. Okay. So this idea that, when you have some slackness, so there's some gap in this constraint from being equal
Ma'am got disconnected again, right?
Yes, I think so.
Okay, I think I again lost everyone. What's happening? Okay, so am I audible now?
Yes, ma'am.
Okay. So, yeah, so this is the problem I'm trying to consider. Can somebody tell me the dual of this? I will just try to connect to my data as well. Okay, any attempts on this dual?
Minimizing of 3x1 plus 8x2, and the constraints are x1 minus 2x2 is less than equal to is greater than equal to 10.
So minimize 3x1 plus 8x2, correct, such that x1 minus 2x2 is?
Actually, ma'am, the second equation is an equality. So won't you introduce one more equation?
Why? Oh, you
Greater than
mean,
equal to
okay.
and less than equal.
Yeah. So you can either do that, or you can say that x2 is unrestricted. So x2 is unrestricted and x1 is greater than 0. So that's also a way to do that. So if you can put greater than, less than equal to and greater than equal to. And so in effect, it is equivalent to saying x2 being unrestricted and x1 is greater than 0, right? Okay, so what about these constraints here? X1 minus
Greater than
2x
equal to 10.
greater than or equal to 10. Okay, yes.
And then 5x1 plus 8x2 is greater than equal to 2, and minus x1 is greater than equal to minus
Minus,
15.
yeah, so minus x1, right? Minus x1 is greater than or equal to minus 15. Yeah, right. So this is the dual for this linear program. So this is actually the same, this dual form which I've written in red. It's the same program that you solved in your midterm exam. Okay, so there was a question where you proved geometrically, right? Geometrically. So let me just, I think I have the solution somewhere. Okay. Yeah. So the solution that you got there, so I think most of you did this. This was a two-dimensional problem, just two variables and couple of constraints, and you solved it geometrically. And what you got was x1 equals 15 and x2 equals minus 73 by 8. I think this was the solution. And you also had the objective was, I think, minus 28. Yeah. Okay, so that was for the dual problem. Okay. So, so the very way in which we have written this dual, right? So if you look at this first constraint, x1 minus 2x2 greater than or equal to 10, how you got that was you took the coefficients of y1. So in some sense, this constraint corresponds to y1. Okay, and this, so let me just write it with a different shade. So this corresponds to y1, and this constraint corresponds to y2, and this corresponds to y3. Okay, so what it means is that, if you now took the dual of this, okay, so it would be like you will get y1, y2, y3, and those are the multipliers for these three constraints, and you will exactly get this maximization problem here. Okay, so let's just keep that in mind. Okay, so now this, let's look at this solution. X1 is 15, X2 is minus 73 by 8. Okay, so did I get disconnected again? Okay, so the screen wasn't updated. Are you able to see the screen now?
Yes, ma'am. Now it's updated, but it wasn't.
Okay. Okay. So, so these, I mean, you saw the way the dual was written, all that was fine, right? And only, I think this part was probably, okay. So anyway, you see the solutions, right? X1 is 15, X2 is minus 73 by 8, and the objective is minus 28. Is this fine?
Yes, ma'am.
Okay, so this one you solved it with in a geometric way. Okay, so now let's just look at this first constraint, x1 minus 2x2. Okay, so the first constraint is so x1 minus 2x2. So that is what, 15 plus 2 times 73 by 8. Okay, so this value is, yeah, it's clearly greater than 10, right? It's strictly greater than 10. Okay, so what this means is that because of complementary slackness, so here this is a strictly greater than, it's satisfying strictly greater than value. So this means that at optimum, the y1 the multiplier corresponding to this constraint, that has to be equal to 0. Okay, so that's just, we are applying this complementary slackness here. Okay, so this was a slack constraint, so you're going to get y1 equals 0. Okay, so that's helping you to get the dual value. Now now the rest of it just follows out, right? So if you look at this dual, the second constraint in the dual, so what you're going to get is 2y1 minus 2y1 plus 8y2 is equal to 8. Okay, so what does it tell you? So y1 is 0, so y2 has to be 1. Okay, so these are the optimum. Okay, I'm just not writing the star every time, but these are for the optimum. Okay, so y2 star has to be 1. Okay, so you got two of these values. Y1 star is 0 and y2 star is 1. Okay, and now if you look at the value of, okay, so now what you need is, all you're left with is y3. Okay, so any thoughts how you can get y3? Am I connected? Okay.
Yes, ma'am.
Yeah, so any thoughts how you could get y3? So you have y1 star is 0 and y2 star is 1.
The first equation.
Yes, first equation, primal or dual? This is the primal, right? So this is the primal. Okay, yeah. Okay, so yes, this is, how would we get that from this place?
y1 plus y1 star plus 5y2 star minus 3.
So y1 star plus 5y2 star minus y3 star.
Minus 3 is less than equal to y3.
So come again. So this is less than or equal to 3, right? So that is this constraint. So can you say that again? Like I didn't catch what you were saying.
Can't we just place the values of y1 star and y2 star together?
Yeah, so then what you're going to get is y1 star is 0 and 5y2 star is 5 minus y3 star is greater than or equal to 3 and y3 star is greater than or equal to 2.
Yes, ma'am.
So okay, so this is a possibility. It has to be greater than or equal to 2. Is there something you can tell about the exact value of y3 star? Can you conclude the value of y3 star? So this is the range of values you're getting, right?
Can you scroll up a second?
Yeah.
So since we are maximizing, so the lowest value that y3 can take is 2, so that's why it's equal to 2.
Okay, fine. So that is a fair enough way. So I was trying to, like go in the direction of, using complementary slackness, but that's fine. This is also fine. You can do this. Now, another thing is, if you apply complementary slackness on the primal problem, right? So here, y1 plus y2 minus y3 is less than or equal to 3. Okay, so this times, this constraint times x1, that has to be equal to 0, right? So now if you look at, okay, so does that help? So x1 is equal to 15, right? Okay, wait a second. So yeah, so y3 is strictly greater than or equal to 0, right? So that, okay, fine. So forget what I said. So I think like what I'm trying to say here is that again it's complementary slackness. It's the other way. So since x1 is greater than 0, so let's just use complementary slackness for this constraint. So what you will get is y1 plus 5y2 minus y3 minus 3. Okay, minus 3. This constraint times x1. Okay, that is going to give you 0. Or you can take it the other way. So 3 minus y1. Okay, so that doesn't matter. The inequalities, which side you consider, that doesn't matter for complementary slackness, because it's ultimately this product has to be 0. Okay, so now you have that the optimum x1 is 15. So this is equal to, this is a value which is like it's not 0. Okay, so that means this quantity has to be equal to 0 exactly. Okay, so that means in effect this constraint has to be tight. So it's exactly y3 star equal to 2. Okay, so this gives that y3 star should be equal to 2 exactly. Okay, so overall the optimum solutions are y1 is 0, y2 star is 1, and y3 star is equal to 2. Okay, so you can do it in different ways, like I think it was Rohit, right, who suggested.
Yes, ma'am.
Yes, so you can also, once you have y1, you can look at the objective and then see like what the value of y3 is. You get some more information about y3, and you can also use other ways. That's also fine. Okay, so overall this is the solution, and let's just verify the value of the objective. So if you substitute this in the value of the primal, what are you going to get? 10y1 plus 2y2 minus 15y3. So 10y1 plus 2y2 minus 15y3, right? So what is this value?
Minus 28.
Minus 28, right? So that was exactly the value of the primal objective. Okay, so in this way, you've not done any simplex, or you've not done any other algorithm, but of course you solved this problem, the problem in red, you solved it geometrically, and you use that geometry to get the solution for the original problem. So that is one of the uses of the dual. Okay, so are there any questions on this example or complementary slackness or anything we saw till date? Is this clear, like how we work this out? Yes, no, you can type on the
Yes, ma'am.
screen. Yes, Rohit. What about the others? I want to hear from some of you. Yes. Okay. Yes, okay. All right. So this is one of the uses. Now, in terms of these values of y star, y1 star, y2 star, and y3 star, there's also another interpretation. So there is this notion of what is called shadow prices. Okay. So what it means is that these y stars are associated with, it's something you can think of as a price that you pay for these constraints. Okay, so it has some intuition in terms of perturbing the constraints. So actually what I'm showing you here is the dual space, whatever the problem from the midterm exam. Okay, so the optimum here, geometrically you found that it was at the point C. Okay, so now if you actually, so this was the original problem in terms of, the feasible region that was, I mean, of course, in terms of what we consider today, this was the dual space. But anyway, if you look at this problem, and now if we think of, suppose some of the constraints are changed a little bit. Okay, so instead of this red constraint, it gets moved a little bit inside. Then what is it that what can we tell about the value of the objective, the optimal conditions or the optimality? What can we say? Is it still going to be minus 28 or is it going to change? Okay, so only one constraint is changed. So is there something we can tell? So we'll see that the dual actually helps us to, make some, predictions about this, or actually you can get an idea of how the objective changes based on the values of the dual multipliers. So I think I will cover this in the next class, and we need a little more time for this. So if there are no other questions, I will stop here. I'll hang back for some time. So if there are no questions, we'll meet tomorrow if you'll be coming. Okay, so thanks a lot for being here.
Thank you, ma'am.
Thank you, ma'am.